learned the algorithm which allows us to perform the search for the special points of a function implemented as an oracle. And this algorithm performs much better than the classical search. So instead of n big iterations, it requires pi divided by 4 square root of n iterations. So we have a quadratic speedup. We understand this is good, but is this good enough? The intractable problems like traveling salesman problem still remain intractable. We need more speedup. And the question is, can we design a better algorithm, a big operator U, which performs better than Grover, which will provide us with, for example, exponential speedup. Love Grover, in his paper with the description of the algorithm, proved that we can't. And to understand the proof, we are going to need some new notations. Omega. We already know this. This is a special point for the classical oracle and a special vector for the quantum oracle. By U here we will denote the algorithm in a very general way, which we believe performs better than Grover's. So here you see the queries to the oracle, and between these queries there are some operators which in Grover's case were all equal to US, but here, since the algorithm is very general, we might expect them to be different. Psi 0 is our initial state, so it's substitute of the vector S. And psi t is the state of the system after t queries to after t iterations. That means t queries to a quantum oracle. And t is the number of iterations needed for the algorithm to perform to obtain some vector which is very close to omega, so we could obtain it after the measurement. So this is vector psi omega. The vector psi omega is the vector, the state of the system after t iterations, and it must be close to omega. And again, by n big, we will denote the dimensionality of our state space, which is 2 in the power n. The idea of the proof is here. We are going to find some vector phi for which this double inequality is true. And on the left here you can see an expression which depends on the number of iterations of our most effective algorithm, T. And on the right we see the expression which depends on the dimensionality of the space, hence the possible number of oracle inputs. And you may notice that both these expressions do not depend on this vector phi. So if we find such phi for which this double inequality is true, then this smaller inequality, which consists of only the left and the right parts here, holds always, which would mean that for the most effective algorithm, the number of oracle queries must be something like square root of n divided by square root of 2. And for Grover's case, we had, as you remember, pi divided by 4 square root of n. So the most effective algorithm is not very much better than that of Grover. And we start with the right side. So first, let's note that for different special points of an oracle, like omega I and omega j, and so the different oracles, our most effective algorithm converges to the different vectors of the state space. And since the algorithm is so effective, these vectors to which it converges must be close to the points of interest. And these points, if they are different, they are orthogonal. So this vector, the final states of our algorithm for different oracles, must be nearly orthogonal. And from here on, we will say that they are not really orthogonal, but just orthogonal. And there are n big different special points. So there are n big of these vectors psi omega. And since they are orthogonal, they form the orthonormal basis in our state space. Now with this, let's take a closer look at this middle part of our double inequality. We have this big sum here and some squared difference, so let's decompose the squared difference. We will have the sum over all omega psi omega squared plus sum over all omega phi squared and minus sum over all omega psi omega phi. And instead of two sums here, as in Euclid space, we will have two different sums because dot product is not symmetric. Like this. And we remember then that for different omegas, we have this psi omega are the elements of orthonormal basis. So we can represent the vector phi in this basis. Let's do it. So phi equals to some x1, x2, etc., x and big. These are the coordinates of the vector phi in this basis psi omega. And each of these coordinates is a complex number, so it has real and imaginary part. Which will denote like this, A, J, and B, J. And now we can put everything we just introduced here. And we notice that these are unitary vectors, so these are ones. So we have 2 and 1s. And minus this sum. Since these are the dot products of a vector on the basis vector, and in this basis we have this representation. So it's sum over j equal to 1, 2, and big, xj plus xj conjugated. And this is just a doubled real part, so we have 2n minus 2 sum over all j from 1 to n big a j.